Yeah. So thank you very much. Physics in the 20th century was dominated by general relativity and quantum theory. From general relativity gives us an understanding of the expanding universe and the extrapolation of the Big Bang. And quantum theory gives us the wonderful phenomenon of superfluidity, which is the phase coherence of the quantum phase over a long distance. And quantum field theory, which tells us the vacuum is a dynamical medium and not just empty thing. And these will come together and offer explanations to puzzles of our time, namely dark energy and dark matter. The overview of this talk is that first, we assume that there's a complex scalar field that exists in a vacuum. And this has been experimentally supported by the discovery of the Higgs particle recently. And the phase dynamics of this field makes the universe a superfluid, as we learned from condensed matter physics. And in short, dark energy will be identified as the energy density of the superfluid. And dark matter will be identified as fluctuations of the superfluid density from its vacuum value. So that's the gist of the thing, and I will develop this in more detail. And in this talk, we first give backgrounds to cosmology, superfluidity, and quantum field theory, and then the synthesis of all these into a cosmological theory. As to the expanding universe, it was based on the data gathered by Hubble a long time ago. That is, the more distant the galaxy, the faster it moves away from us. And general relativity gives us the understanding that this is due to the expansion of the fabric of space-time. It is like we were living on the surface of a balloon. And when somebody blows up the balloon, then points of the balloon move away from each other. And the farther the 2 points away, the faster they are moving away from each other. And Hubble's law says that the velocity of recession is proportional to the distance. And Hubble's parameter, which measures this velocity, which is the fractional rate of increase of the universe, of the radius of the universe, is 1 over roughly the lifetime of the universe. Now, so we can verify Hubble's law by measuring galactic redshift, which measures the velocity, and its distance. And if I plot the distance against the redshift, which is the velocity, Hubble's law is the straight line on the plot. And all the old data, which concerns more closer, nearby galaxies, they all lie in the straight line. But more recent data on supernova show that there's a deviation of the straight line. And that deviation shows that the more distant galaxies, that is, galaxies from an earlier era, move more slowly as dictated by Hubble's law. And this says that the universe, the expansion of the universe is accelerating. And people attribute this to an unseen dark energy that drives this acceleration. And this is dark energy. And then, as to dark matter, it was observed that the dust that's circulating around a galaxy like Andromeda, which is rotating, they have a velocity. And you can attribute that velocity to the mass of the galaxy. Now, if you just take the observed mass of the galaxy, you would expect that velocity to drop off like curve A with distance. But the observation shows that it doesn't drop off. It follows curve B. So the difference between A and B is explained by hypothesizing that there's dark matter in the galaxy, something that we cannot observe, but which exerts an influence on this rotation curve. And more recent evidence for dark matter comes from the observation of collisions of 2 clusters of galaxies. It's called the bullet cluster. Here, the 2 galaxies sort of collide, and you can see the red stuff is a hot gas, which is visible through X-rays. But there's some trailing behind these 2 galaxies, the blue stuff, that is not visible to any electromagnetic emission, but is only detectable through gravitational lensing. This shows evidence that there's a halo around galaxies, and this is so far the most convincing data for the existence of dark matter. And so, but with some analysis, the energy pie charts of the universe would be 70% dark energy and 25% dark matter, and the rest is just a small slice. So most of the energy in the universe, according to this view, we don't understand. Now, superfluidity. Superconductivity is a manifestation of superfluidity. It was first discovered in 1908 by Kamal Honors. Here he's shown with his assistant in this lab trying to hunt down an annoying short circuit, which they couldn't fix for 2 weeks. And finally, they threw up their hands and said, this is superconductivity. And it was 1908. It was not until 1950 that it was explained by Ginzburg and Landau in terms of the quantum phase coherence over macroscopic distances. And they described this by introducing a phenomenological order parameter, which is a complex scalar field. You take a field which has you write in the form Fe to the I sigma, where sigma is the phase. The superfluid velocity is the gradient of this phase over space. And in superconductivity, the gradient of sigma is the supercurrent. And this was 1950. And this, in fact, is the Higgs model with this, in fact, is the Higgs mechanism. And in quantum field theory, the vacuum is a dynamical medium with fluctuating quantum fields. And this is actually real because its effect was directly observed by Lamb and Cush in terms of the Lamb shift and the anomalous magnetic moment of the electron. Now, in a standard model of particle physics, there's a complex scalar field in the vacuum. That is, it fluctuates about a finite value, non-zero value, and that's a Higgs field. And there will be other fields also in grand unified theories. A complex scalar field in the vacuum, whatever its origin, makes the universe a superfluid, as we learned from Ginzburg and Landau. What a very important thing about quantum field theory is renormalization. This was in the seminal work of Freeman Dyson, 1949. He deals with the following problem. In quantum field theory, there are virtual processes with a momentum spectrum that extends to infinity. Now, you must be cut this off at some high momentum, for otherwise, the integral you calculate in your theory would diverge. The question is, how do you deal with this cutoff? Freeman Dyson showed that the electron charge, or the physical charge, can be expressed in terms of the bare charge, which is what you put into the Lagrangian, as a bare charge times a factor. And that factor contains a cutoff. You do not know the cutoff. You do not know the bare charge, but you don't care because all you care is the physical charge. So you just take that from the experiments. That is called renormalization. And with this trick, which people thought was a trick at that time, one computed the Lamb shift. It was Weizskopf, Schwinger, and Feynman successfully computed the Lamb shift. It took some time to discover the physics behind renormalization. And that's due to the work, a long series of work due to Gell-Mann and Low, which defined the so-called beta function. Carline and Semantic, which shows that the cutoff is a scale parameter. And to Bock-Lyubov, who coined the term renormalization group, that the scale transformation forms a group, and that group is represented by renormalization. And finally, the grand synthesis by Wilson. In Wilson's in Wilson's formulation, if I imagine the momentum spectrum, which is on the left, it extends to infinity. When you define a theory, you say that you cut it off at some cutoff lambda 0. That defines a theory. Because if you did not cut it off, you don't have a theory. You have divergence. So you must cut it off, this lambda 0. This lambda 0, which is usually defined at a very high momentum scale, but you work at a much lower scale. So you want to lower that scale to a lower scale at which you work. The degrees of freedom behind lambda 0 and the scale at which you work must be hidden. They are not thrown away, but you must hide them so you don't refer to them. And the way to do this is to change the value of the coupling constants in your theory. Wilson show you how to do this. So that a scale change, and as scale changes, one must adjust couplings so as to preserve the theory. So that the system's appearance changes, but its identity is preserved. And that's the physics of renormalization. And this then makes all the coupling constants dependent on the scale of the theory. This is particularly important when you consider the Big Bang, when the scale of the universe changes very rapidly. So in a scalar field, you have the Lagrangian given here, and the important thing is the potential. That specifies the theory. The potential is usually written as a power series in powers of the field. And renormalization makes the couplings, the lambdas, a function of the cutoff. Therefore, the whole potential is a function of a cutoff, or the length scale. And this dependence is, as I said, important. So during the Big Bang abuses theory, the potential will be changing rapidly. So the appearance of the theory will change very rapidly during the Big Bang. So one could represent this graphically. In the space of all Lagrangians, if you postulate potential, you postulate Lagrangian. This is the space of all Lagrangians. There's a fixed point at which the theory is scale invariant. And that is that in a scalar field that corresponds to the massless free field. When you change the scale, it does not change. That's a fixed point. At that point, the cutoff is infinite. There are trajectories coming out of this. That is, if you coarse-grain the theory, it goes out on a trajectory. In a so-called ultraviolet trajectory, this will go out along this trajectory in the coarse-graining direction. This trajectory corresponds to a system that is so-called asymptotically free. That is, if you go in the reverse direction, the energy increases. So that as the energy increases, you go towards a fixed point, and the coupling vanishes. That's called asymptotic freedom. On the other hand, you could have infrared trajectories. And those trajectories are not trajectories at all. It is a limiting trajectory. It goes in along the entire trajectory, the cutoff is infinite. So those are really boundary lines between phases of the system. You cannot really be on them. You can approach them very closely. And so there are these two kinds of trajectory. If you have the ultraviolet trajectory, you have a system that has asymptotic freedom. And if you're on an infrared trajectory, it is as if you're always at the fixed point, and the theory is trivial. So in scalar field cosmology, during the creation, let's ponder the creation. At the Big Bang, lambda is infinity, and there was no interaction. The universe was a Gaussian fixed point, represented by the red dot in the picture. And the potential in the scalar field is identically zero. The Big Bang starts if when the system is displaced infinitesimally from the fixed point. That starts a Big Bang. It emerges along some direction in the space of all Lagrangians as on a renormalization good trajectory. The direction corresponds to a particular form of the potential V. If the trajectory happens to be an asymptotically free one, then it spawns a universe. And if you happen to land on an ingoing trajectory, then you have never left a fixed point, and that's triviality. So I suppose we are here because at that moment it chose a trajectory that is asymptotically free, and it develops a universe along this trajectory. So now, if you consider scalar field, what is the potential that would correspond to an asymptotically free trajectory? It can be shown that if the potential is a polynomial, then it's always trivial. And there's a unique asymptotically free potential. That's the Huang potential. It's a Kuma function, a hypergeometric function that has exponential behavior at large fields. In fact, if you take the equation satisfied by this potential and reduce it to 2 dimensions, you get the well-known Sine-Gordon theory. And this is the potential we're going to use because it's the only asymptotically free potential. So let us write down. So now let's put together, form a cosmological theory. There are 2 equations. First, Einstein's equation, which gives you the curvature. It's driven on the right-hand side by the energy momentum tensor of the scalar field. And the second line is the scalar field equation, in which V depends on the cutoff. And we consider a universe so small that the density is uniform. So fortunately, we can use a very simple metric, the Robertson-Walker metric. In this metric, there's only one parameter. The radius of the universe is a scalar, A. Now, the scalar field has a cutoff. That's the only scale in the theory. Since there can be only one scale in the whole universe, lambda must be equal to 1 over A. This means that gravitation cuts off the quantum field theory. And this is dynamical feedback. The gravity provides cutoff to the scalar field, which generates the gravitational field. And when you put this together, you've got a set of simple closed equations that form an initial value problem. I illustrate this with a real scalar field. There are 3 unknown variables, which depends only on the time, because the universe is uniform. There's A, the radius of the universe, H, which is the Hubble parameter, and phi, the scalar field. But there are 4 equations. The 4th equation is a constraint equation that constrains the initial values. And that equation has to be preserved by the, where's this noise coming from? That must be preserved by the equation of motion. Otherwise, the system would be overdetermined. And therefore, the constraint equation must be preserved by the equation of motion. And for this, we require an extra term that is usually not present in the usual cosmological theory, and this term here, which is absent if the V is independent of the scale, which is what people usually assume. But if V depends on the scale, you need this term. And this term can be traced to a trace anomaly in the energy momentum of the scalar field, which I will not go into. Anyway, here's the general picture. There's a Big Bang, but we cannot start at the Big Bang because the equation becomes singular at A equal to 0. So we move it a little bit from the Big Bang, maybe 10 to the minus 43 seconds from the Big Bang. We start there. The initial condition, we assume that the vacuum field is already present. That is, the universe is already a superfluid. Now, the universe could be created in a hot normal phase and then make phase transitions to the superfluid phase. Then that all happens in this interval, and we don't know anything about that. We just start from this point. And here's a numerical solution. The equation is so simple, we just solve it in MATLAB. The left-hand figure shows you the potential, the Kerson Huang potential, which shows spontaneous symmetry breaking. And the solution for the Hubble parameter H shows that this is a log-log plot. It shows that asymptotically, it approaches a power law with a certain slope that depends on the parameters, initial conditions, and so forth of the model. And then below this is the picture for A, the radius of the universe as a function of time, and the scalar field, which oscillates, which is, for those working in this field, it's very different from the usual assumption of so-called slow roll. So the main thing is that H, the Hubble parameter, goes like T to the minus P, where P is some index dependent on the parameters of the model. That means that the age of the rate of the universe is exponential T to the 1 minus P. And so the expansion is accelerating, therefore there's dark energy. However, the Hubble constant decays in time. So this solves the usual puzzle that the presently observed Hubble constant is very small on a natural scale, on Planck scale. And why is it so small? This explains it by saying that because it decays in time. That it may be natural at the Big Bang, but in 15 billion years, it has decayed to the things that we observe. So this explains dark energy. Now, this model is only true near the Big Bang, but the suggestion that H obeys the power law may be something that would survive the model. So it will be interesting to compare this prediction, the power law, with data. Here I plot the distance, which is dl, of a galaxy divided by the z, which is the redshift parameter, as a function of z. On this plot, the Hubble's law is the horizontal line. And the black data are reliable data from supernova observations. You can see that there's dark energy because they deviate from Hubble's law. And the prediction of the power law is the curve A, with a certain chosen P. If we change the index P, the shape of A does not change, but this slides it up and down. It goes to B, for example. The large Z data is from Gammaray Burst, which are not as reliable. However, they all show a systematic deviation from A. They seem to go to another regime with a different index P. So if this is true, then maybe there was a crossover transition in the universe from one regime to the other, and the crossover was completed about at this point, and that was about 7 billion years ago. So this at least shows that the prediction of dark energy seems to pass the test of comparison with data. Now, an important question is cosmic inflation. Inflation is that we must create enough matter when the universe was small enough so the matter see each other, so that they maintain a uniform density, so that even now, when the matter fell out of each other's horizon, they still maintain a uniform density. So you have, in that very short time, you have to create all the matter in the universe. How do you do that before the universe gets large? That's one problem. The second is a decoupling of matter scale and the Planck scale. In our Big Bang equation, there's only one scale, the Planck scale, that comes from Einstein's equation, from the gravitational constant. But however, once you create matter, the matter brings in a new scale, the QCD scale of 1 GeV, which is the mass of the proton. It just comes on spontaneously. How do you separate these two scales, 1 GeV and 10 to the 18 GeV, in the equations? And this is a problem. In the equation, they're all entangled. You have to separate them. And we cannot do this with a real scalar field. So we consider a complex scalar field. Now, if the complex scalar field, which is just two real scalar fields really, if you regard them as completely uniform, you don't solve the problem. And therefore, we think of new physics that you get when you have a complex scalar field. The new physics is superfluidity, and in particular, quantum turbulence. We maintain that it's the quantum turbulence that creates enough matter for later creation, nucleogenesis, and the creation of galaxies. Now, in the complex scalar field, one of the interesting aspects of a complex scalar field is there are vortices. A vortex is a flow of the field around a line, so that if you go around in a circle enclosing that line, the phase changes by a multiple of 2 pi. So if I write phi as f e to the I sigma, and identify the superfluid as gradient of sigma, the gradient of sigma integrated over this loop has to be 2 pi n. And if you set n equal to 1, you have a 1 quantum vortex. And this is quite different from the classical vortex and turbulence because it is quantized. All vortices are the same, like hydrogen atoms. They're quantized. And in our work, we cut off the wave. The field function is a constant at infinity. It goes gradually to 0. We just use a square cutoff. So that in this picture, space is imagined to be filled with flux tubes. So it creates a kind of wormhole in space. And outside of that space, the gateway is uniform. And we treat this wormhole as a new system. That's the vortex system. The vortex dynamics I can just briefly explain. The simplest vortex is a vortex ring, a smoke ring. It has its own natural translational velocity. And the velocity is inversely proportional to the radius of the ring. So the larger the ring, the slower it moves. Now you can, this enables us to understand the motion of a vortex line, a vortex curve in the equation. At any point, I can draw a radius of curvature at that point. And the velocity of this line would be perpendicular to the paper, with the velocity inversely proportional to the radius of curvature. So the smaller the radius of curvature, the faster it moves. And if the radius of curvature is gentle, it moves very slowly. So the whole curve, you put in a liquid, makes a very complicated self-sustained motion. And that's the basics of vortex dynamics. An important property of vortex is the reconnection. When you have two vortex lines approach each other, they could cross. Before crossing, on the upper level, they are moving very slowly because the radius of curvature is relatively large. But once they cross, you create two cusps, which theoretically has 0 radius. So the two cusps would spring away from each other theoretically at infinite speed. This is the mechanism we rely on to create matter, because this cusp receding would create 2 jets of energy, and that will create 2 jets of matter. It is interesting that this is also the mechanism for the creation of for the ejection of matter from the sun and the sun's corona. And there you rely on the reconnection of magnetic lines into the vortex tubes. And that is the only mechanism I think of that could convert a large amount of potential energy into kinetic energy in a very short time. Now, if these things are, if you have vortex lines and they reconnect often enough, it becomes quantum turbulence. Here's a simulation. You put a heat current through a system to continually generate large vortex rings, and then they reconnect when they touch. The upper level begin no connections, and you have 3 connections, and you have 18 connections, 844. Finally, when you have 14,000, 1,500 degree connections, it looks like a mess. That system has a fractal dimension of 1.6, whereas the line has 1. So it changes the character, and that's called quantum turbulence. So quantum turbulence is vortex tangle with a fractal dimension. So now we can put this together into a cosmology with quantum turbulence. The ingredient is a scalar field, which has a uniform modulus F. And the phase dynamics is manifested via the vortex tangle L, which has a uniform density. It is important that we maintain uniformity because we're going to use the Robertson-Walker metric. Once you go away from that, you cannot do anything in general relativity. And the matter is created in the vortex tangle. So the variables are on the left side. A, the radius of the universe, F, the modulus of the scalar field, L, the vortex tube density, and rho, the matter density. And the equation of motion is obtained as follows on the left-hand side. A dot is from Einstein's equation. F dot is from the field equation. L dot is from a phenomenological Vinen's equation for quantum turbulence. And rho dot is then from momentum conservation. So the only thing new is Vinen's equation, which looks like this. Let L be a vortex tube density, length per unit spatial volume, which is regarded to be constant, uniform. And L dot has a growth term and a decay term, and they have different powers, and that the different powers are argued by dimensional analysis. Vinen proposes phenomenologically, but it was derived by Schwartz from Vortex Dynamics, and is verified by experiments in superfluid helium. So we just use this. So now, instead of the old equation, the 3 equations on the left side, we now have 1 to 5 equation. The original 2 equations are sort of extended on the first 2 lines, but we have 2 new equations, one for the vortex, the other for matter. Now these 2 systems know each other only through those variables enclosed in those red boxes. Now if you look at this more closely, I don't want to go into this. You may, in some approximate, regard those boxes as constants. When you do this, these 2 equations decouple. So you have one set of equations, the top 2, describing the expansion of the universe. The bottom 2 describing the vortex system and the creation of matter, and with phenomenological coefficients that sort of are constants you can adjust. So this is decoupling. So in cosmic inflation, in our picture, there's a vortex tangle, which is quantum turbulence. It grows and eventually decays because of the expansion of the universe. All the matter needed for galaxy conformation was created in the tangle. So the inflation era is a lifetime of quantum turbulence. After the decay of quantum turbulence, the standard hot Big Bang theory takes over, but with one addition, that the universe remains a superfluid. So here's the picture. You have the energy of the vortex system as a function of time. We design a model. It grows to a peak and then decays, and the lifetime of that peak is the duration of inflation. The area under that curve is the total amount of matter being created. So that at the end of this process, you have created a certain amount of matter ready for use for creating galaxies. One can put in numbers to make it come out that the radius of the universe increases by a factor of 10 to the 27 in 10 to the minus 30 seconds. And the matter created is 10 to the 22 sun masses. And all the galaxies are created outside of the vortex tubes, because only outside the vortex cores is there a scalar field. So the vortex cores remain empty of galaxies. So, a summary, we have a Big Bang, and this is an era of quantum turbulence with inflation, and that is valid to about 10 to the 10 to the minus 26 seconds. That's valid to the value of our model. Beyond that, you you go for the hard Big Bang theory with superfluidity. And then there's a long way, 10 to the 5th years before you get a CMB. So we're talking about a very small length of time after the Big Bang. However, if you take the hard Big Bang model and all that and put in the superfluidity, what consequences will you have in the present observable universe? Just imagine this is superfluid. There is a survey of the Galactic Survey. At the center of the Earth, you stand out, you measure galaxies, measure the distance and velocity in a thin wedge of observational wedge. And there is about 7,000 galaxies. The remarkable thing is that in this map, there are big holes in the galactic distribution. On a scale of, on a large scale, they're uniform, but on a scale of, say, 100 million light years, they're big holes. For example, there's something they call the stick man on the left-hand side. There are holes of 10 to the 7 light years. Now, knowing that there are flux tubes in the vortex tube universe, there would be a very simple explanation. Those cores are just cores of the vortex lines. At creation, they were of Planck scale, but they grow with the expanding universe. So in 15 billion years, they have grown to 10 to the 7 light years. And there are no galaxies inside, because the scale was not in there. And I just quickly put together a simulation of intersection of 3 vortex tubes, and you have a stick man there. But of course, you have to analyze more seriously. And Thursday PM in a parallel session, Dr. Abel Yang of NUS will present a serious search for these flux tubes in galactic data. And now these huge flux tubes that's left over, they would reconnect. And when they reconnect, that will be a major event because the energy release will be very great. And you have 2 jets of energy coming out from that. And this could be the Gammaray Burst, which is a few events per galaxy per million years, lasting milliseconds to minutes. And the energy output in 1 second is the sun's output in the entire life of its billions of years. So this could be a candidate for that, the reconnection of gigantic macroscopic flux tubes. And then, if stars all rotate in the superfluid, they would generate vortices. In particular, a black hole, which has very high angular momentum, would generate a cage of vortex lines enclosing itself like the conception illustrated on the left. And it's very suggestive that at the center of our galaxy, one sees these so-called non-thermal filaments. And inside there's a black hole. Now, these non-thermal filaments could be those vortex tubes. So that's a possibility to be investigated. Finally, dark matter. On the left, you see the scalar field as a function of distance. And in a quiescent vacuum, it's just a constant everywhere in the vacuum. Now, you put a galaxy into this medium, the galaxy would disturb the fluid. It would pull the fluid to the galaxy, forming a platform, a plateau. That plateau is a halo around the galaxy. And that we can detect through gravitational lensing, and that is dark matter. So now I have some computer simulation based on a 2D phenomenological scalar field obeying a nonlinear Klein-Gordon equation in curved space with the galaxy as external source. To be convenient, we use 5-fold scalar potential because the cutoff is not rapidly changing here. So you can use anything convenient. So we are calculating the response of the superfluid to a galaxy is being dragged through it. Now here it is. Number 1 is the creation of the galaxy. When you create a galaxy, there are rings of transient waves emitting from the galaxy. You can see that. And in galaxy 2, the galaxy starts to move upwards, but the ring is still centered around the center, the transient. The galaxy is at the center, a dark spot, and there's a white halo forming around the galaxy. And then you can see that the halo follows the galaxy like a soliton, whereas the ring of transients propagate and finally they hit the boundary of our computational system and reflects back. And that's the end of the simulation. Here is the 2 galaxies colliding head-on and passing through each other. On slide 1, 2 galaxies approach on the vertical direction head on. And then they look at the white stuff is the halo. Look at how the distortion of the halo. It's all superfluid hydrodynamics. And that is what would create the so-called bullet cluster. And they merge in 4, they merge 5, 6, and then finally they separate in 8. And here are 2 galaxies are passing each other at a finite impact parameter. The superfluid in between will be sheared into rotation. And to do that, they have developed vortices. Those 2 black dots are vortices that enable them to rotate. And so the vortices in the superfluid is an interesting thing. And this slide illustrates the vortices that's developed around a rotating galaxy. If you rotate it fast enough, the vortices will form layers of dots around this galaxy. And around each of those points, the phase of the field will change by 2 pi. And if you plot the contour plot of the phase of the field, you get a chrysanthemum on the right-hand side. Each black line is a string across which the phase jumps by 2 pi. And this research was done here. Here are the people of my research team, and there are the references. And I think I have time, finally, to show an animated version of those pictures I show you. So I'm going to do that. Here's your galaxy moving upwards with the transient waves going out. Now the transient hits the boundary. And this is the colliding galaxy head on. And this is the galaxy passing each other with a finite impact parameter. You see the vortex activity being there with those 2 black dots. Perhaps let's see it once more.